Okay, so this gets to that question of what can we do to prevent intercepting? So one thing we can do is we can do end-to-end encryption. We can use TLS to encrypt web traffic at one end and decrypt it at the other end. So as it flows through the network, there are just well-encrypted bytes. If TLS is a good protocol, and it mostly is, then your data, people can't see what your data is. If you use SSH for remote login, the same thing is true. The bytes go through, but people can't see what's going on. So the question with this is, we sort of see what it protects, the contents of your data. What does it leak? What does this not get at? Yes?
Everyone in the middle still knows that you're connecting to an IP on that end.
Right.
TLS has something called SNI, which leaks the host.
Right, so this leaks who you're connecting to. So if you're connecting to torrentfreak.com, then it becomes pretty clear that you're connecting to some torrent website and you're likely going to download some torrents and perhaps pirate some things. So who you're connecting with gets leaked via this mechanism. Other things that might get leaked. So something else to get leaked is sort of the size and pacing of your traffic. So the size of packets and when you send packets is leaked. And this is important because it turns out, suppose you're connecting to a proxy like an SSH tunnel. Many people here, I'm sure, have used SSH tunnels to get around various rules. Suppose the thing is that you can see by the size and pacing of the packets who you're connecting to. So people have shown if you're connecting to a tunnel like an SSH tunnel, and then you connect to Google or Facebook, people who just see the encrypted traffic to that tunnel can tell that whether you're connecting to Google or Facebook, because they can see that the packet lengths and the timing of packets and when you send requests and how big the responses are very different for different web servers. And so just seeing this length and timing information leaks a lot about what you're actually doing. The actual data, we don't know, we don't know what Google search you're doing, but we can sort of perhaps get a guess of, is it a really popular search term and there's lots of response? Is it an unpopular search term that's very narrowly targeted? So we leak this, and this is called traffic analysis, because we're just looking at the traffic without the content and inferring something about your activity. The other thing that can go wrong here is that TLS assumes that the servers on either side haven't been compromised. And so an easy way around this is to basically attack somebody's computer and install logging software on that computer. So a lot of people have used, for example, secure messaging services on their phones. Well, the way around this is you use a vulnerability in the phone to just record things locally and see all that communication before it's encrypted or after it's decrypted. So this only sort of protects you from the edge of the phone to the edge of the other server, but it doesn't protect you inside your devices. The other thing that can go wrong is we have to look at where things are actually encrypted. So this is a picture of Google. So what happens at Google, or it used to happen, when you connect to Google, you'd connect over TLS. It would go to Google's web servers. Google's web servers would immediately decrypt the traffic, and then everything inside Google would be decrypted. So this means that if you can get a surveillance machine inside Google, you can see all the unencrypted traffic. So this is somewhat unlikely. I think Google takes a lot of pride in security. The problem is there's this piece here in the middle where you see data center at the top and data center at the bottom and data center over here. Google runs different data centers that are physically distributed. So they have data centers in California, they have them probably in Texas, and near Chicago, and Massachusetts, and China, maybe not China, Hong Kong at least, and Europe. And between those different data centers, they don't actually have their own cables there. They often lease cables from other companies, from AT&T or Sprint or Verizon. They're dedicated fiber optic cables they own, but they belong to another company. And so government agencies can spy on those fiber optic cables. And Google, for a long time, did not encrypt that traffic. So when you went to Gmail and you went to California and then it went to Texas to find your data, that traffic between California and Texas would go over an unencrypted link that was not controlled by Google, that could be spied on by a surveillance agency. And this was something that was sort of revealed by the Edward Snowden document leak a bunch of years ago. So the key takeaway here is that we really need to, this model of we have a firewall, and once we're inside the firewall, everything is secure. is somewhat true within your own physical data center where you control everything, but as soon as you sort of leave your building and go outside, and you have a cable that you don't sort of control and have armed guards standing over, somebody can break into that cable and see all the traffic going by. And so you really need that to be encrypted. So the other thing that was brought up before is this question of connectivity. How do we, we can tell who you're connecting to. So, if I'm a government that doesn't want you connecting to Facebook, then I can see you're going to Facebook. And so what can we do about this? And this is important. There's a lot of countries where there's heavy censorship. So if you're an anti-government activist in one of these countries and you want to communicate using some banned communication mechanism, you might want to be able to evade your government censors to be able to get access to this. So how can we hide connectivity information? So the way to think about this is what is the information we want to hide? We want to hide that it's my computer connecting to some other computer. So we want to make it look like to a censor, I need to communicate with someone. So I want to make it look like I'm communicating to some other machine on my end, not the illegal destination. And at the destination side, we'd like to make it look like it's some other machine, not mine, connecting there. So we want to sort of hide the two ends where there's communication, so that somebody can't sort of connect my machine to that remote server. So there is a system to do this called the Onion Router, or Tor. This was actually developed by initially the U.S. Navy Office of Naval Research, I think. So this was a government designed and developed project, despite what you may think. The U.S. government puts a huge amount of money into secure communication because they really want this capability for their own people. So the basic idea here is that if you want to connect from, say, IP 1234 to something else, instead of connecting directly, we will connect to some other somewhat random machine in the internet. In this case, we're going to connect to machine 7891. 7891 will then connect to 8911. 8911 connects to 9112. 9112 connects to 5678, finally. And so we connect through these things, but if you're intercepting traffic or doing surveillance, all you see is this traffic between these Tor nodes. You don't see the traffic from my IP address, and you can't connect it to this final IP address. So this sort of obfuscates or makes unclear who is communicating to whom, because we're sending it through these Tor routing links. So it does slow things down because you have to send packets across the internet multiple times, but networks are pretty fast, and if you're really worried about your security, then slowing things down might not be so bad. So under the covers, here is sort of what it looks like. It's actually done with encryption so that nobody sort of knows what the actual route is because each level is encrypted. So you start off with your basic packet that has the source and destination IP addresses. You then encrypt it with the public key of the first node in the network. So this is 9112. This is called a Tor node, and you're going to encrypt it with the public key of that Tor node. And you're going to put a new source and destination. So the source is that node, but there's a new destination, which is the next node, and then we encrypt the whole payload with the next destination. So the idea is that at each level, each of those nodes, even if it gets compromised, somebody breaks into it, sees everything, you can't actually see where the traffic is going because the data is encrypted with the secret key for some other traffic. So then we apply this again at the third level. We're going to encrypt in the key for 8911, send it to 8911, and then the final place we encrypt it to 7891 with a source and destination. And so we have this layering where we start off sending it to 8911, 8911 sends it to 9112, 9112 we'll send it along, and then the final packet will get delivered to the real destination. So this will sort of guarantee that each of these layers is encrypted differently. Anything you look at is just encrypted TLS traffic, and it's between two nodes, and you can't tie it back to any particular user in a particular way. Any thoughts? Yes?
What are these core nodes? Just random machines scattered across?
They are just random machines. A lot of universities, I think we may have one. I know that when Tom Ristenberg was a professor here, he wanted to get a Tor node installed. The nice thing about running one is that you can then look at all the traffic and sort of research how people are using it. So there's some benefit to security research on having one of these locally. But yeah, they're really just standard servers that have a relatively fast processor to do the encryption and have network connections. And then the Tor system as a whole, you have to know in advance what are the various Tor nodes that are available that are up and running and what their public keys are. And then on the client side, when you want to send a packet, you're basically going to pick some set of these Tor nodes, get their public keys, and then create this onion of encryption around that packet to sort of create the encrypted packet before you send data. And then each Tor node, all it does is receive the packet, decrypt it, see where it's supposed to send it, forward it along. Yes?
And at your host machine, you build the route originally?
Yes.
And you send it out?
So the send, it's called source routing because the original, only at the source do you actually, you have to sort of pre-create all that encrypted piece, so you have to know who's going to see the packet. So it does mean if any one of those machines goes down, then you're going to be able to stop, you're going to stop sending traffic.
Also, when you get a response from the final destination, and if they're still using the Tor network as well, will it?
Well, so let me create a little bit. So I said the source node, it's actually the first Tor node you send it to. So when you send it to a Tor node, that first node can see where you're sending it, and it can build the onion for you. So you as a client don't have to build the onion if you don't want to. And so the responder, Facebook can just respond to a Tor node thinking it's a normal client. That Tor node, first Tor node will build the onion and then send the packet along. So that first step of the traffic isn't really secured, but once it gets into Tor, it's secured. Yes?
So if you decide to run a Tor node and the exit nodes, what are the legal implications that your computer is going and accessing certain things?
That's an excellent question I don't know the answer to. I do think there is some risk there, but I think my understanding is that Tor is relatively well established at this point, and the institutions that take it on, have ample legal, ample sort of legal teams like big universities. But I think it's an excellent point, so generally sending packets to and from someplace is not illegal. It's sort of viewing them as a human or, what you're doing with them. For example, because the same thing could be said for an ISP that has a switch, right? It's just like a network switch. Should your ISP have legal liability for routing your packets to some illegal destination when it knows nothing about what you're doing? So that is kind of the argument. Yes?
What would be the legal implications of listening to the traffic on the Tor node?
Well, so, generally, it's not legal to eavesdrop on people. I don't know in this case if there's an issue. Certainly, generally, when somebody sends you a packet, you're allowed to look at it because they sent it to you. And certainly, ISPs do lots of deep packet inspection on their own to sort of look for, all kinds of problems, to sort of find security problems. And so, generally, I think that lots of kinds of inspection are legal. So, for example, we have researchers in the department who have traces of every packet coming and leaving the university, and so they have access to the complete set of data, what everybody on campus is doing across the network. And typically, what they have to do is they will have a machine that collects the traffic, they anonymize the traffic, so they strip out IP addresses and other things, and then they store the data itself on this particular machine, and then you can send an analysis to this machine to sort of look at the data, but the raw data, whatever he's doing, can't leave that machine. And part of the issue is at a public university, there are open records laws that say that anybody can kind of sue the university and ask for records. So this trace of packet is a public record in a way at a public university. So that's why it's treated very sensitive. At private universities, they can do whatever they want, so their researchers have much more access to all the data from people. But generally, like storing network traces, I sort of walk back what I said. Storing network traces is a fairly widely accepted non-illegal practice, which is why you want to do things. So what an adversary sees, as I said, is just either traffic from a Tor server to, which could be any client, we don't know which, to a particular destination. Hopefully it's over HTTPS, so the traffic is encrypted at the end also. Or they see traffic between two Tor nodes having no idea where it came from and where it will go. So the question is, how secure is this? Should you trust this? Any thoughts? on what the vulnerabilities are. So between the Tor nodes themselves, I think it's pretty secure because there's lots of traffic from different users mixed together. It all looks like just encrypted traffic. You really can't tell it apart at all. But at either endpoint, when you're sending regular traffic to the first Tor node, or when the traffic leaves Tor and goes someplace, that is where there's some risk involved. So there's actually a case at Harvard where there was a student sending bomb threats using Tor. He was using Tor to connect to an email service. He thought that using Tor would sort of conceal who he was. What happened is that the mail service he connected to had logs of who was connecting, and so the FBI could see somebody who's connecting over Tor. And so the FBI said, well, probably this is a person at Harvard. So they went to Harvard and they looked at the logs, the network logs, to see who was connected, and they could see there's only one person at Harvard using Tor during this particular period, right? And so, you know, lo and behold, that one person was the kid who sent the bomb threats. And so the important lesson here is that, you know, Tor is great, but if somebody can figure out what Tor node you're likely using, or and you're the only person using it, then you're sort of exposing yourself. So there's sort of safety in numbers to some extent. When you're doing you're only person using some obfuscation mechanism, you're at risk because people can tell it was you. So that doesn't mean it's not good. It just means that it's not perfect. So the thing to know, whenever you connect to UWNet or EduRoam, the university is logging that it was you who logged in, and they know physically what network you're logging into. And if something happens, they can potentially trace those packets back to you at a particular time in a particular place, because all that information is often saved. Any more questions on Tor? Okay, so Tor is a relatively sophisticated system. It's pretty good. There are other simpler mechanisms. You know, some are sort of single hop proxies where you connect to some anonymization service and it forwards packets for you. So it's sort of like a one hop Tor network. There's anonymous remailers where you can email something to a remailer and it will remail that mail to someone else on your behalf, but sort of stripping out who it came from. And these have been sort of, had more legal problems. That the FBI has seized these services or shut them down because they're sort of concealing information. The other thing to think about is, I've talked mostly about the government doing surveillance, but companies are also doing a lot of surveillance. I think we all know that Google, Facebook, Microsoft, Amazon, keep petabytes of logs on everything we do so they can try to, provide better service or get us to buy more. But the law says that basically anything you expose to a third party is sort of, you are making it public. The expectation is you're making it public. So if you make a phone call, you are using your phone, you are telling the phone company who you're calling, that makes it a public record because you expose the phone number you're calling to the phone company. If you connect to a web server, you're exposing to that web company what you were doing, so that becomes a public record to some extent that you connected to the web server. And so this means that if there are records created by any company about what you're doing, they are available to law enforcement, and they don't need a wiretap because this is sort of public information to some extent. So as an example, AT&T, again, our favorite phone company. Mostly it's just the original phone company, so it sort of gets in trouble the most. But it had a Hawkeye database, and it basically kept a record of every phone call everybody was making, the time of the call, the length of the call, trillions of phone call records over many, many years that was available to law enforcement without a warrant. They could go in and ask, who has Mike been calling recently, without having to show that I was actually implicated in some crime. And again, this is because it's sort of considered a public record once you actually make a phone call. Similarly, bank records, when you expose that you're buying something to a bank, those bank records may not be considered official secrets because you told the bank you wanted to buy something by the act of using a credit card. Similarly, companies get a lot of requests. This isn't data from Google on how many requests they get. This is sort of how many requests they get, how many different accounts they're looking at. So you can see in 2017, it was something like, over 100,000 different accounts. They got requests from law enforcement agencies around the world to give information about what these accounts are doing. So if you send, a nasty email threatening to kill the president or something, then Google might get a request for information about who you are to learn more about what you're doing, show people your email to see if you're a real threat or not. So another thing that happens is censorship. What I've talked about so far is surveillance, which is just looking at people, but just like intrusion detection, intrusion prevention, the flip side is that you can sort of stop people. So you can censor who they can have access. The Golden Shield project in China is perhaps the most famous one of these, but the idea is, you have some country where Facebook and Google don't operate, or you can control who operates in your country. You don't want your citizens to access YouTube, for example, which happened in Pakistan. And so you can put filtering equipment at the edge of your country, which you still control, and you can sort of filter any traffic you don't like. So there's something like 100 countries that do some level of filtering. There's a bunch of countries that sort of do a lot of filtering. China, Saudi Arabia, Belarus are examples that do a lot of filtering. And a lot of it is sort of filtering anything that is either considered amoral, so a lot of pornography, things that are considered, a lot of places will filter torrent files for sort of anti-piracy efforts, and then things that are sort of generally anti-government or seditious, or you're worried about your citizens working together to overthrow the government, that kind of things gets filtered also. The way this is done is pretty straightforward. This is really just like a firewall in some cases, looking at IP addresses. If you see somebody connecting to the IP address for Google, you shut it down. So as an example, I was in Beijing a couple years ago at a conference, and from my cell phone, I couldn't get to any Google properties. No Gmail, no Google Maps, no Google.com. When I was at the hotel and I had registered who I was on an authenticated network, then I could get to Google properties. And so there are sort of firewall rules or censorship rules in place that limit where I could access and what I could access. And this can be at every level again. This can be deep packet inspection, so you can look at particular words. You can do protocol filtering to sort of detect the Tor protocol. So one thing a lot of people try to do is try to basically take one protocol and make it look like another protocol. So can you take Tor traffic and make it look like DNS traffic or Facebook traffic or something like that, so that you're communicating and the sensor doesn't know you're communicating, but you're actually sort of communicating with some rogue service. So here's the basic ways you get around these. With IP filtering, you can use a proxy. So if you have some server outside the censorship area, you send a packet to it, and then it will connect to the actual machine you want to talk to. So SSH tunneling is an obvious example of this. So DNS filtering, sort of preventing people from looking up certain DNS addresses. Here, if you just change which DNS server you're using, Google has a public DNS server that they run to explicitly avoid DNS filtering and make sure you get to their version of what is the real source of every site. Then you can evade this kind of filtering. For URL filtering or packet filtering, here you can encrypt everything using TLS or SSH, because people can't see the URLs. So your sensor then has the option of sort of dropping and killing all encrypted traffic or letting it through. And enough things are encrypted right now that sensors typically don't want to prevent all encrypted traffic. And for protocol filtering, I mentioned obfuscation techniques where you sort of make the protocol look like something else. It turns out that it's actually hard, and if you apply machine learning, you can pretty much always undo these obfuscation techniques for now. So that's sort of a open research topic on how you really hide communication. So as a quick example, the Golden Shield project in China, probably the best known, does many of these things. So it will do IP filtering, DNS filtering and redirection. It does URL filtering on what URLs you can get to. If it sees a packet it doesn't like, what it will do is send a TCP FIN packet. So it'll basically close the connection down when it sees a packet that it thinks is something it doesn't want to let through. So you might be able to start a connection, but then once you search for Falun Gong or something like that, Falun Gong, sorry, it might at that point decide, you know what, I'm going to shut this down, kill the connection. So as a user, you just see that you went to a service and it started breaking. It's not like you get a big red sign that says you've been searching for something illegal. You just sort of things stop working. And then there's also protocol filtering, so things like Tor don't work. So the question is, you know, as a community, as a society, as an academic community, what do we think and what do we do about this? This is sort of an open question. So there's a lot of research on circumventing censorship and circumventing surveillance. There's also a lot of research on how to do high-speed packet filtering, how to build, you know, because we need it for security, right? Intrusion detection and prevention is the same technology as internet censorship. And so if you can build one, that same technology builds the other one. And so how do we sort of grapple with what these capabilities can do? So, you know, one thing we can do is we can try to have data that's always encrypted. So encrypting end-to-end is good because it means no matter where you are in the middle, the traffic has been encrypted. So for example, instead of having Google store your mail in clear text, if Google stored your mail encrypted and only the recipient could decrypt it, that would mean that Google couldn't reveal, even if somebody came to it, what your mail said. The other thing to think about is that, you know, companies used to be, at one point, companies would very willingly go along with government requests. This is sort of the AT&T approach, and other big tech companies have done this also. But, you know, users now have complained more. People who work at companies, notably Google, complain a lot when Google cooperates with the government on surveillance. And so there's a lot more pushback, and there's a lot more negative perception here. And so there is a tension in society of, you know, we sort of value when the FBI can stop a terrorist attack before people get killed. We also don't like the FBI sort of spying on us when we think we're doing nothing wrong. So there's sort of broad, open questions here of what is the right policy we should have. Any thoughts or comments? Okay.